In the last session, we discussed about the acid with higher concentration reacts faster than the acid. As the concentration of the reactants increases, the number of two collisions, which is equal to stoichiometric coefficients in a, then according to law of mass action, the rate will be increased by 4 times. The concentration of the reactant will be reduced by half. Then the reaction speed will be reduced by 4 times. Is doubled. The speed of the reaction is doubled, or it takes only half the time to complete 30 seconds to decompose. Rate of reaction, when practically determined, is directly proportional to first power of concentration of hydrogen peroxide. Concentration of hydrogen peroxide as order of reaction. Hello students, welcome to Learn It. In the last session, we discussed about 6 factors which affect the rate of reaction. So let's begin with the concentration of the reactants in detail. Consider hydrochloric acid with 2 different concentrations. When zinc metal is added, the acid with higher concentration reacts faster than the acid with the lower concentration. By this we understand that the concentration of the reactants influence the speed of a reaction. The question comes, how? As the concentration of the reactants increases, the number of collisions increases. As the number of collisions increases, the products will be formed sooner. As we discussed before, this relationship between the concentration of the reactants and rate first observed by Gato Goldberg and Peter Waag. So they gave the law of mass action. They studied many chemical reactions and noted that by increasing the concentration of the reactants, there will be more collisions and the reaction will be faster. That's why they named it as a law of mass action. According to law of mass action, the rate of chemical reaction is directly proportional to product of molar concentration of the reactants. So let us consider a hypothetical reaction, that is, reactants are converting into products. So according to law of mass action, the rate is directly proportional to concentration of the reactants. Here, square bracket indicates the concentration. When we remove the proportionality sign, then rate is equal to K into concentration of reactants. Here, K is the rate constant or specific reaction rate. The value of K is different for different reactions, and also the temperature. So remember, when temperature changes, rate constant will change. So which will influence the rate? About this we will discuss in detail in the later part. So this expression is called as rate equation or rate law. Remember, rate law is an expression or equation. So let's take one example as we discussed before, that is decomposition of hydrogen peroxide into water and oxygen. As the reaction is balanced, so it is called as balanced chemical reaction. So when we apply law of mass action to this equation, then rate is directly proportional to concentration of the hydrogen peroxide into concentration of the hydrogen peroxide, because there are 2 reactant molecules are involved. So rate is equal to K into concentration of hydrogen peroxide bracket square. So this is rate law or rate equation for the decomposition of hydrogen peroxide. So this is the way of writing balanced chemical equation, and this is the way of writing rate equation or rate law. When we compare the rate equation with the rate equation given by law of mass action, there is a little lag. That is the power of concentration terms. So that's why these two scientists elaborated the law of mass action and gave a new statement. That is, at a given temperature, the rate of chemical reaction is directly proportional to the product of molar concentration of the reactants raised to power which is equal to stoichiometric coefficients in a balanced chemical equation. This is why the rate law for decomposition of hydrogen peroxide is rate is equal to K into square of the concentration of hydrogen peroxide. Let us analyze this rate equation. Consider rate is equal to x moles per liter per second. It means if we take hydrogen peroxide 1 mole, then rate is equal to K into 1 square, that is equal to x moles per liter per second. If we take the 2 moles of hydrogen peroxide, then rate is equal to K into 2 square, that is equal to 4 times than the x moles per liter per second. So if we double the concentration of the reactant, that is hydrogen peroxide, then the speed or rate of reaction increased by 4 times. If we take concentration of hydrogen peroxide, that is equal to 3 mole, then rate is equal to K into 3 square, that is equal to 9 times the rate of the reaction when we have taken the 1 mole of hydrogen peroxide. So it means that if we increase the concentration of hydrogen peroxide by 3 times, the speed will be increased by 9 times. In conclusion, we can say that, so consider any amount. It may be 1 mole, it may be 0.5 mole, it may be 0.1 mole, or it may be 10 mole. So we can calculate the rate of the reaction and it will be having certain value. And if we double the concentration, then according to law of mass action, the rate will be increased by 4 times. It means the time taken to complete that reaction will be reduced by 4 times. So if we triple the concentration, then the speed will be increased by 9 times, or the time taken to complete that reaction will be reduced by 9 times. And we can also say this, as the reaction proceeds, we know the concentration will be decreasing. So consider there will be a certain reaction speed in the beginning. So after certain time, the concentration of the reactant will be reduced by half. Then the reaction speed will be reduced by 4 times. It means the reaction speed is 4 times slower than what it was in the beginning. If the concentration of the reactants is reduced to 1/3 of its initial concentration, or you can say that if the reaction is completed 66.66%, then the rate of the reaction or the speed of the reaction is reduced by 9 times. So these all predictions are based on law of mass action. When scientists perform these reactions in the lab, they got different result. If the concentration is doubled, the speed of the reaction is doubled, or it takes half the time to complete the reaction. So if the concentration of the reactant is tripled, then the speed will be increased by 3 times, or it takes 1/3 of the time to complete the reaction. For an instance, let's take 1 mole of hydrogen peroxide, which is equal to 36 gram containing Avogadro's number of molecules. So let's consider it takes 1 minute to decompose. If we take 72 grams, then it only takes 30 seconds to decompose. If we take 108 gram, then it takes only 15 seconds to decompose. This decomposition of hydrogen peroxide is performed under a catalyst, manganese dioxide. Otherwise, it would take many days. With respect to decomposition of hydrogen peroxide at definite temperature, the rate of reaction when practically determined is directly proportional to first power of concentration of hydrogen peroxide, which was different than the law of mass action, which was second power of the concentration of hydrogen peroxide. This power of concentration terms in an experimentally or practically determined rate equation is called as order of reaction.